All right, so last lesson we talked about calorimetry. We discussed how you can get information from calorimetry experiments, how you can use those data to determine the enthalpy of a reaction. And today we are going to talk about two more ways that you can calculate the enthalpy of a reaction. And one is using Hess's law, and the other one is using heats of formation. So in today's lesson, we will discuss Hess's law. We will discuss how to apply Hess's law to solve problems and how to calculate heat of a reaction using enthalpies of formation that you will find in tables and in charts that will be provided to you, or you can look up in a textbook. So Hess's law states that the enthalpy change, that is the delta H value of either a physical or a chemical process, depends only on the beginning and the end conditions. So in other words, it only depends on what you started with, your reactants, and only depends on what was your product, where you ended up with. The pathway of how this happened, the different processes that happened in between your starting at your reactants and ending at your products doesn't really matter. All that matters is your start and your finish. So the enthalpy change for the conversion of reactants to products is the same whether the conversion occurs in one step or in many steps. And this law allows us to determine the energy of a chemical reaction without actually directly having to measure that exact reaction's energy, without having to know exactly for that specific reaction. We can do this by either combining reactions algebraically that will add up to result in that equation, or by using enthalpy of formation of reactions values from a table, from a chart. So the first method, the method where we can combine chemical equations algebraically and just add them up, you add equations with reactions of known enthalpy changes. So you take reactions whose enthalpy changes are given, are known, and you add them together in a way that the net result at the end, once you've added them up, ends up being the reaction that you're interested in. And this may need you to manipulate those known equations by either maybe you need to reverse them, maybe you need to multiply them by a coefficient. And if you do multiply them by the coefficient, obviously you need to multiply the delta H value by the same number. Or if you reverse it, you will need to change the sign from positive to negative or negative to positive for that delta H value of that reaction. So to better understand what we're trying to say here, let's look at a couple of examples. So let's say you're given one example where you're asked, what is the enthalpy of formation of 1 mole of diamond from 1 mole of carbon? Okay, so the question is formation of 1 mole of diamond from 1 mole of carbon. So you figure out that this is the reaction that you're being asked to do. Carbon in its solid graphite state going to carbon, which is also what diamond is made out of. Both graphite and diamond are made out of carbon, going to carbon in its solid state, but diamond. And you're asked to figure out what is the enthalpy of formation here. And just to remind you again, when there is that degree sign, that not sign, this is called not, it indicates that the reaction is happening under standard conditions, so standard temperature and atmospheric pressure. Now, by having to look at this, we need some known equations. And these are some of the known equations that you would be given in this sort of a question, or maybe you're given a table with a bunch of known equations and you're supposed to go in there and figure out which are the equations that will be useful to you to solve this target sequence. It's almost like finding a puzzle, solving a puzzle. So you're looking for pieces that once you put together and add up will give you this final reaction. So say you're given this top one that's measured from a calorimetry experiment, and this reaction is known to have a delta H naught of minus 394 kilojoules. Then you also might have this one. And this one has a delta H naught of minus 396 kilojoules. So how can we use these equations to arrive at this equation? So I'll give you guys just a couple of minutes to stare at this, and then I'm going to go to the next slide. So I want everyone to just look at these and consider, if we were going to just add these equations up, how are we going to do it in order for terms to add up, cancel each other, and we end up with this? Okay, just think about it for like a few more seconds, and I'm going to flip to the next slide. Okay, so we can use these known equations to obtain the target sequence. For example, these are those known equations that I had. First, we can reverse the bottom equation. So we can take this and flip it around so that our first equation remains the same, because if we look at our target equation up here, our target equation was we want graphite going to diamond. So this first equation already has graphite on the left side, on the reactant side. So we keep it that way. Now we want diamond to be on the right side, on the product side. So if we take this equation and flip it around, reverse it, so that we've got CO2 going to diamond and O2. And by doing that, we will also have to change this negative sign to a positive sign here. Then we can see that, okay, we've got our carbon graphite and we've got our diamond on the correct sides that we want them to be on. Graphite is our reactant, diamond is our product. And then we see that, okay, our CO2 terms cancel, because here's it being the product, here it is being the reactant, we can cancel them out. Same with our oxygen term, it can cancel out from opposite sides of the equation. And it adds up to being that target equation that we were looking for. And then we just algebraically add up these delta H naught values, and we end up with a delta H naught of plus 2 kilojoules. So what I want you to notice here is that you can reverse equations. If you do so, you need to make sure to also reverse the sign of the delta H value. And if you need to multiply, say, one of these or both of these by some coefficient to help cancel out terms, then you have to multiply this value by the same equation. So these are things I want you to keep in mind. Okay, so any questions about this first example that we go to? Was it clearly explained? Is it easy to follow? Okay, so as I said, in this type of equation, these things will be given to you either in the body of the question or in the form of a table, say on your midterm or your final exam. Let's look at a second example. In this second example, we're asked to calculate the enthalpy for this reaction. So our target sequence is nitrogen gas plus 2 oxygen gases goes to 2 nitrogen dioxides. And what is the delta H here? We are being asked. So we can use these two equations that we can find in tables, or it might be given to us. So one of them would be that nitrogen gas goes to 2 NO2, 2 NO, nitrogen oxide. So here, so essentially you're choosing equations that have the components that you're looking for, and so the reactants that you're looking for, and either the or the product, and then something in between that might cancel out in another equation. So for example, in these two equations, we can take the first equation and keep it as it is, and we can reverse that second equation so that we have 2 nitrogen oxides going plus an oxygen molecule goes to 2 nitrogen dioxides. And when we do this rearrangement, obviously we will remember that because we reversed it, we are going to reverse this sign as well. And then we cancel the components that cancel out, the terms that cancel out. So the 2 NO and the 2 NO will cancel out. And then we add things up. So then we have N2, we write it down here. We have 1 O2 plus another O2. So we have 2 O2s, we write it down here. So we are adding things. And then our 2 NO2 gas, we write it down here. And then we just mathematically add up our delta H values. Our plus 180 minus 112 gives us plus 68 kilojoules. Okay. And it's really important in these equations to pay attention to, is it a gas? Is it a solid? And make sure we really have the right equation. Okay, because sometimes they can be in different states. We might have, for example, water as a liquid state. It might have an L here if it was water, or it might have a G, gas, if it was water vapor. So you really need to pay attention, and I really want everybody to get into the habit of writing down the states below like this, okay? When you're doing these types of equations. And I think that that is another example of a very simple way of calculating the enthalpy, the delta H. Let's look at a third example. In this third example, we are given, asked to calculate the enthalpy change for the formation of 1 mole. So we make sure we notice that it says for 1 mole of butane gas. So remember, this is butane gas. C4 makes it a bute, and then 10 hydrogens all around it. Butane gas from its elements. Okay, from its elements. So the target sequence then, if it's from its elements, is that what are the elements in butane gas? Well, there's carbons, there's hydrogens, there's 4 carbons. And then there is 5 H2s. Because remember, hydrogen comes in 2s, hydrogen gas, and comes in 2 hydrogens bound together. So 5 H2s gives us 1 molecule of butane. We're asked to find what is the enthalpy change for the formation of a molecule of butane from its elements. Okay, that's our target sequence. We're asked to find this. And the following known equations are provided to us. We are told, given that we have equation 1, equation 2, and equation 3, and these are the delta H's for each of these. Can you find us what is the delta H for this target equation? Okay, So we begin by examining what do we know, what have we got, what are we told? Okay, let me just move this back a little bit to make sure we understand that this is 13 over 2. This is a fraction value here, okay? This is 13 over 2 O2s, okay? So we are given this target equation. So we are given that we have butane plus 13 over 2 O2s goes to 4 CO2s plus 5 H2O. And I didn't write it here, but I fully expect everybody to have that there. That should be there. And I'm just going to put it there to make it very complete for everybody. And our second equation is that carbon plus O2 goes to CO2. Our third equation is that 2 H2 molecules plus 1 O2 molecule goes to 2 H2Os, okay? And we see that we have delta H values for it. So we begin by examining and see, okay, using these three, how can we arrive at this final point here? So first thing we can do is our first equation has got this butane, but it's on the wrong side of the equation. So right away, that gives us a clue that we should reverse this to get it on the product side, because in our target sequence, that's on the product side. So we reverse it. We've got butane on the product side. And by doing so, we also have to pay attention to the sign of our delta H, because now it has to go from minus to a plus. Then, since we need 4 moles of carbon in the target sequence, see here we have 4 more moles of carbon in the target sequence, we take our equation 2, which has carbon on the reactant side, just exactly where we need it, but we see that we need 4 of them. Here in this equation, there's only 1. So we multiply equation 2 by 4. So we do 4 times equation 2. So it becomes 4 carbons plus 4 O2 molecules makes 4 CO2 molecules. And please note now that our enthalpy value has also now been multiplied by 4. It's 4 times of this value. So we have up to this point. Now we notice that we need 5 moles of hydrogen gas in our target sequence. So here we have 5 hydrogen gases. Do we have that yet? No, we don't. But look, we have it in our equation number 3. Is it on the side that we need it on? Yes, it is, but it's just not the number that we need it on. We need 5, and in this equation, there's 2. So in equation 3, we have 2 molecules. If we multiply equation 3 by 5 halves, by 5 over 2, then we will get 2 moles. And don't forget that then we have to multiply the enthalpy also by 5 over 2. Okay, so we multiply the equation by 5 over 2, and we end up with 5 H2s, 5 over 2 O2s, and 5 H2Os. Okay. Now we add it all up together. So we line them all up as we have here. We put the correct H values in front of everybody, and then we start crossing out the elements that cancel each other out. So the 4 CO2 here cancels out with this 4 CO2. The 5 H2Os cancels out with this 5 H2Os. The 5 over 2 O2s cancels out with this, adds together with this 4 O2 to cancel out our 13 over 2 O2. And we add it all up to end up with our target sequence. And we can also add up all of these delta H naught values, this change in enthalpy formation, to end up with the enthalpy change of the formation for this target sequence. So this was another example of a question that you might be asked something similar on your midterm. And you will have plenty of opportunities to practice with these questions because they are present in some support questions that you're given. So here you're given these equations and you're asked to calculate the delta H for this reaction. Same with this one. So here's a couple of chances to practice, and more of these questions are also available in your key questions at the very end of this lesson. And yeah, some more practice questions here. So you got altogether 5 sets of questions that you can practice with and really sharpen up your puzzle solving skills here. Now let's talk about these standard enthalpies of formation. The standard enthalpy of formation is the quantity of the heat energy that is absorbed or released when 1 mole of the compound is formed directly from its elements in their standard state. So that not value here draws your attention to it being standard state. And by standard state, we mean 25 degrees Celsius, room temperature, and, or not room temperature, standard temperature and pressure, 100 kilopascals. And what do we mean by the word formation here? By formation, we mean the formation of a substance means written as the product of a chemical equation formed directly from the elements involved. The substance in question is always written with the coefficient of 1. Here are some examples of what do we mean. For example, the formation of CO2, it's from its elements, from carbon and from oxygen. Same with carbon monoxide, it's from carbon and from oxygen. And remember, because this is for just one molecule, for 1 mole of a compound, I guess maybe it's a good thing that I should highlight when 1 mole of a compound. So if you notice, all of these compounds, there's no coefficient, it's just 1. So there's not 2 CO2s, 5 COs, 6 H2O2s, it's 1 because you're looking for the formation of 1 mole of compound. So here are some examples of these. And keep in mind that by definition, the delta H formation of an element in its standard state is 0. So the delta H formation of an element is 0. By element, we mean carbon. So if we were asking for a delta H formation of carbon, well, that's 0. But some elements, such as hydrogen, such as oxygen, fluorine, bromine, iodine, nitrogen, and chlorine, are all diatomic elements, means that they exist in pairs. For example, H occurs as H2. Oxygen occurs as O2. Nitrogen occurs as N2, and etc. So that the delta H formation of an element in its standard state is 0. And most elements, other elements, are solid in their standard states. Noble gases, as well as these diatomic elements that we were just naming here, like the hydrogen, oxygen, nitrogen, fluorine, chlorine, etc., are gases in their standard state. Bromine and mercury are 2 that are liquid in their standard states. So maybe I can highlight these so that we can pay attention to that. And the standard state for a substance in solution is at the concentration of 1 mole per liter. So if it's in liquid, if it's in solution, it's at 1 mole per liter. So, like I said, the delta H of an element is 0 since an element is in its most fundamental form at standard conditions. And so the standard enthalpies of formation of things like oxygen gas or solid sodium metal or liquid mercury metal, for example, are all 0. Okay. So how do we write these formation equations? So we can first write 1 mole of the product in the given state. Then we can write the reaction elements in their standard states. Then we can balance our equations. So let's look at an example. For example, here's our 4th example in this lesson. Write the formation equation for liquid ethanol. Okay. So here you're told that they're looking for liquid ethanol. So you write ethanol on your product side. You make sure you put the liquid state with it. And then you look at, okay, what have we got? We have got 2 carbons, 3 hydrogens, and oxygen. So then you put the right numbers to make sure it balances out. So you want 2 carbons. So you put your 2 here. You need 6 hydrogens because 5 and 1, we need 6. And hydrogen is a diatomic gas. So you put 3. That makes 6 altogether. And then you need only one oxygen. And because oxygen is a diatomic gas, you put a coefficient of 1/2 in front of it. And there you have written the equation. You were asked to write the equation for the formation of liquid ethanol. This is the equation for the formation of liquid ethanol. Now, how can we use, say, an equation like that if we know how do we use these standard enthalpies of formation to calculate the enthalpy change? So the enthalpy change for your target equation will be equal to the enthalpy of formation for all the products minus the enthalpy for formation of the reactants. And this is an equation that summarizes what I just said. Okay, so all the enthalpy formation of the products minus all of the enthalpy formation for the reactants. And this symbol, many of you know, it means the sum of, the total of the enthalpy formation of all the products and the total of enthalpy formation of the reactants. You subtract those. And these standard enthalpies of formation are found in a table at the end of this lesson. And these standard enthalpy formations will be provided to you on a test or an exam. And sometimes these enthalpy problems may take more than one step. So, and it's useful to keep these following relationships that we've talked about in mind. For example, the enthalpy change in a system is equal to the heat transfer to or from the surroundings. So delta H is equal to Q of surroundings. Or the total amount of thermal energy absorbed or released by a chemical system is equal to MC delta T. Or that the molar enthalpy change of a reaction is equal to the enthalpy change of the reaction per mole of the substance. So these are important concepts to keep in mind as we're looking at these problems. So let's take a look at yet one more example. What is the molar enthalpy of combustion of methane fuel. So methane, as you guys remember, would be CH4, and it's a gas, CH4 gas. So, and it's a combustion reaction. So you know it's got to be reacting with oxygen. And because it's a combustion reaction, again, because we know from studying combustion reactions a couple of lessons ago, that it goes completely into carbon dioxide and into water. So knowing all that we know, just being asked this, we can write this equation. We can write that methane, which is CH4 plus oxygen, goes to these products. So these reactants, methane plus oxygen, go to these products, CO2 gas and H2O. I think this should also be gas. Okay, I will clarify that because it's actually, there are values for both liquid and gas, and I can't remember which one I grabbed right now for this, but that, like I said, it's important to pay attention to whether or not there's liquid or gas. But anyhow, and then we make sure to also balance this equation. And balancing it takes 2 O2s plus 2 H2Os to balance this equation out. Then we use our equation that the enthalpy change for our target equation equals the enthalpy of formation of our products minus the enthalpy of formation of our reactants. So here we've done our products minus our reactants. So let's look at it one term at a time. So our first product is 1 mole of CO2 minus 395.5 kilojoules plus 2 moles, 2 times 285.8 kilojoules per mole minus now our reactants. And our reactants were methane and oxygen. So 1 mole for methane and 2 moles for oxygen. So methane, the value of formation is minus 74.4 kilojoules. And for oxygen, it's 0. 2 moles times 0 kilojoules per mole. And we know it's 0 because looking back at what we were talking about in our slides is that by definition, the enthalpy of formation of an element in its standard state is 0. So oxygen is an element, its standard state is gas. And here we have oxygen in its standard gaseous state, it's a gas. So we know that we are okay to give it 0. The correct thing to do is to give it a value of 0. Then it's just careful math. You multiply these out, moles and moles cancels out, and you end up with kilojoules. Again, 2 times this value, moles and moles cancel out. You add this side, and you end up with this value, minus, and you do the same for this side. You add it all up, so minus negative 74.4. You do your math carefully, and you should end up with this. And that is the delta H of combustion of 1 mole, right? 1 mole of methane. So it becomes minus 890.7 kilojoules per mole. And then there's always a mark given for writing a proper statement for these questions. You write that the molar enthalpy of combustion of methane is minus 890.7 kilojoules per mole. Okay, so that is another example. Now I'm just going to scroll to the end to make sure that I do have these values at the end of this. Yes, I do. Okay, so here's what a table that you might be given could look like. It has all different compounds here, and you have to pay attention to their state, whether they're liquid or gas or solid. For example, over here, you have water vapor, so H2O gas, and you have H2O liquid. You have to make sure you use the correct value. So looking back at the question, because we had H2O liquid, I made sure to take the value for H2O liquid. If I had H2O gas, I have to make sure to take the value for H2O gas. So have to pay careful attention to these things, okay? Let's go back to our example. Yeah, so that 285.8 was for liquid H2O. One more example. Actually, before I start this one more example, was there anything here that anybody had a question with that was unclear?
No.
No? Okay. So yeah, you guys on your own time, go through these, do the support questions, do the key questions. If you have any questions, you guys let me know. I'm happy to connect with you by email, or we can set up a Zoom call or something and go through this. I really want everybody to get what they need from this course. So let's look at one more example. So in this example, you're asked, what mass of octane is completely burned to cause the heating of 20 grams of aqueous ethylene glycol, which is an automobile coolant, from 10 degrees to 90 degrees. And the specific heat capacity of aqueous ethylene glycol is given as 3.5 joules per gram degree Celsius. And you're told that you can assume water is produced as a gas and that all the heat flows into the coolant. And the balanced equation is even given below. So you don't even have to think about how to write up this, combustion equation. But suppose you didn't have this equation written up. So ethylene glycol is an automobile coolant, and octane, we know, is the oct part, we know it's 8 carbons. So we can immediately picture that this is an alkane with 8 carbons, and every single one of those bonds around the carbon has got hydrogens attached to it. So the formula for it, even if we weren't given this combustion equation, we could easily write this up ourselves. Here is octane, and it's a gas. Plus, we know it's a combustion equation, so we know there's got to be O2. We know that at the end, you're going to have, in a combustion reaction, nothing left but CO2 and H2O. You're given that this is a completely burned. So it's a very complete combustion reaction. And then it's just a matter of writing the right numbers, right coefficients to make sure your equation is balanced on both sides, making sure that you have as many carbons on this side as you have on that side. You have as many hydrogens on this side as you have on that side. You have as many oxygens on the reactant side as you have on the product side. You balance it out. There you go. So if on a test or on an exam, you are asked to write this, and even if you weren't given this equation, you should be able to write, what is this combustion equation? That should be no problem at this stage. Then you start thinking about, okay, all the other things that I'm told. So I'm told that this is what we're going to burn, and it's going to cause heating of this ethylene glycol from this temperature to this temperature, so you can figure out the delta H. You're given the heat capacity of ethylene glycol, And so first we want to calculate the molar enthalpy of combustion of octane. We want to know, so if we burn this octane, first of all, how much delta H, how much heat is produced? So delta H is equal to, we use the equation where we know we can take the sum of the delta H formations of all of our products, minus the delta H formations of all of our reactants. And we can do the math and we can end up with the delta H. So these are values that we can look up in that table. We can look up the value for the formation of CO2 gas from that table at the end, and it's 393.5. We can look up the formation of, this time, notice it's H2O gas, okay? Assume water is produced as a gas. Okay, so we make sure that we grab the value from the table for water in the gas state. And so on and so forth. So for this octane, the value is there for 250.1. And then for oxygen, well, oxygen is 0. Remember a couple of slides ago? Delta H of an element in its standard state is 0. Then we do our math, we end up with our delta H value for the combustion of octane. Now we have to assume that the heat produced by this reaction will be absorbed by the ethylene glycol, that engine coolant. So we say that the delta H of the octane, all of this heat produced, will go directly into the coolant, so it's equal. But we wonder, first of all, what is the molar mass of octane? The molar mass of octane, we need to know, is, so we have 8 carbons in octane, we have 8 hydrogens, and we can look up these values. 8, and the molar mass of carbon is 12.1 grams per mole. These are values that we can find on the periodic table. For hydrogen, it's 1, or more accurately, 1.01 grams per mole. We have 18 of those, we have 8 of those, multiply it, add it, you end up with the molar mass of octane is that much. So therefore, we solve for how many moles of octane do we have? And we know through this relationship that we can find out how many moles of octane we have. So we do our 20 grams of aqueous ethylene glycol. So, and this is just a reverse of this equation. So this is actually that same equation of Q is equal to MC delta T. And Q is equal to delta H times however many moles. But we need to know however many moles because we can use that together with the molar mass to find out how many grams, what mass is what we were being asked, what mass of octane. So we know that we were given 20 grams of aqueous ethylene glycol. We know that the temperature of that ethylene glycol changed from 10 to 90. So the change delta T is this 80 degrees. We are given the specific heat of ethylene glycol, which in this case we can convert from joules to kilojoules because our value here is in kilojoules. So we want to make sure our terms of kilojoules cancel each other out. Or if you choose to keep this value in joules, then you want to make sure you change this value into joules as well, because you need these terms to cancel out, these units to cancel out. Then you do your math and you end up with 0.0011 moles of octane. That's how many moles of octane we have. So if you have this many moles of octane, What does that mean in grams? What mass of octane is that? Well, the mass is equal to the number of moles divided by the molar mass. And we figured out what is the molar mass. And we can take the number of moles divided by the molar mass, and we end up with 0.12 grams. And then we write our nice statement at the end that says 0.12 grams of octane is burned in order to heat 20 grams of coolant, being ethylene glycol, by 80 degrees Celsius. All right, we can follow that along. Now, this was an example of a question that has multiple steps in it. In this case, you were given the equation. You didn't have to figure this out, but this could easily be figured out too. You could be asked to write the combustion equation and then to figure out the rest. So you can see there's many steps, but the many steps follow very logically. You figure out what you need to solve for, and the steps that you need to solve it. We have a few support questions here that you guys can practice with. And finally, we have your key questions. Okay, key questions. All right, so yeah, here is the table at the end, which you can use to.
Excuse me, ma'am. Slide 16 and 17 are the part of key questions.
Let me just see. 1, 2, 3, 4. Yes, they are. 5, 6. Yeah. You have key question is 1, 2, 3, 4, 5, 6. There's 6 key questions in all. Yeah. It all goes to continue. Yeah. So actually, this is a good point that you just raised. I have a feeling maybe some of you, because I know when I was marking the key questions that you submitted, some of you didn't submit some of the key questions at the end. And I don't know if you didn't want to do those questions, if it was too difficult, you decided to skip them, or you didn't realize that those were also key questions that have to be handed in. So I have marked and returned in your shared folders, everybody's assignments, everybody who's handed stuff in. So please look. If you see that you didn't hand in a question by mistake, I'm willing to accept them still. If it was an honest mistake and you honestly didn't realize that you were supposed to hand it in, if you want, you can still hand them in. I will correct them and I will add your mark in. Otherwise, if you missed questions that you didn't hand in, I'm sorry to mark for them. Obviously, there can't be any mark, but if this is something that has happened by mistake, by you not realizing this question was part of the key questions, please go ahead, look through your assignments. If you see that there's questions you should have handed in and you didn't hand in, get them into me now, okay? Get them into me by this weekend and I'll still mark them, okay? All right, so we have finished the material for this lesson now, but we still have a good hour of our class left. Now, looking back, has anybody got any questions? Has anybody been trying to solve any of the support questions from previous lessons and having problems with it? If you like, now is a really good time for us to go through those and look at them. We can do that. Or if you feel like we have time this hour to go back to previous units and review some of those lessons, if you like. Why don't you guys let me know what you need? Okay, so I'm hearing silence at the other end. And my conscience is not clear. I don't want to waste this hour that we have left together. So I think I would like to go back and at least work on some of the things that I saw were some problems and some issues that I noticed you guys were having. Maybe, okay, let's go back to even I'm trying to think what I can give you guys. You know what? I am just going to open up our reviews. Let's go back to our previous unit. Okay. So let's look at, so let's go through naming some of these compounds. Let's try and do some of these support questions together at least. How about that? How about we try maybe naming some of these hydrocarbon compounds together? Hang on 1 second while I try and find the right. Okay, because I noticed some of you were having trouble with naming of compounds. Okay, so okay, let's try naming some of these compounds. I would like to know how you guys feel about that. Okay, so gosh, I'm thinking how to do this. Maybe, okay, let's start with just naming them because I think it's trickier to draw structures here on. Okay, so let's start, maybe can somebody take a stab at giving the name for this first compound here?
Is it pentane?
It is 1, 2, 3, 4, 5, pent, and it is pentane, yes.
Okay.
Okay. How about, does anybody want to take a try at somebody different naming this compound here? So we've got 1, 2, 3 carbons. We notice a double bond in there. Anybody want to try other than, sorry, who was it that just answered? Was it Sasan?
Yeah, that was me.
Okay, great, Sasan. So somebody else, give it a stab. So we've got 3 carbons, and if we recall, 3 carbons, you give it the prefix of, let's see, there is meth, eth, and then let's go back and have a quick review. Let's go back and have a quick review. Okay, so meth, eth, and prop, if you remember. Those are the, right? So prop. And since we see that that had 3 carbons on it, it's a prop. And then because we see that it has a double bond, double bonds are given the ending "ene." So instead of propane, this would be propene. And suppose it had 3 bonds, it would be propine with the Y and E.
Sorry,
Okay.
with the Y, right? Propene.
What propine? This is propene, but
Naming it.
yeah, for naming it, yes.
So for naming it, we should write it with Y, right?
For this one, it would be an E. Because if you
Okay.
remember back to our slide here, and I'm trying to find the right slide. Unsaturated hydrocarbons, right. So the ending "ene" indicates the presence of a double bond. The ending "ine" indicates the presence of a triple bond. Okay, so for example, this would be butene. For example, this would be hexine because of its triple bond. Okay. So this would be propene, right?
Can I try C?
Absolutely.
So would it be butane?
C would be butine. Now, because the triple bond is here, it could also be here. So you have to tell me what butine, put a number in front of it.
Di?
Di would mean it has 2 of something. Does it have 2? So butine,
Oh,
no, it hasn't got 2, but yes, the name starts with butine. So you have to tell me which carbon is this triple bond on. So far you've told me that it's 4 carbons. So 1, 2, 3, 4, good. You've told me it's an ine. So I know there's a triple bond in there somewhere. Now you need to tell me where. Which carbon is it on? So let's count the carbons. Carbon 1, 2, 3, 4. And since it's symmetric, it doesn't matter. We can even count it from this side. 1, 2, 3, 4. So either way, the double bond is between the 2 carbons, carbon 2 and carbon 3. So how do we name this? We name the first carbon that it's on, carbon 2. So this is 2-butene. Okay? 2-butene is what we have here. Does that make sense?
yeah, I just said di because I thought it was, yeah.
Okay, yeah, perfect. I'm just trying to think of where to put this now. Okay, next one's a pretty straightforward, easy one. Anybody want to try this one?
Nonane.
Nonane, perfect. Yes, thank you. How about E? Anybody want to try E? E. So we count the carbons first of all, so we know what prefix we should give it. 1, 2, 3, 4, 5. So what sort of a prefix does something with 5 carbons get?
Pent.
Pent, thank you. So pent, and then what do we see? What else do we see here that's important?
There's 2 lines, so it's in.
So it's a double bond, so it's an ene, exactly. So this is called a pentene. Exactly, thank you very much, pentene. Again, F is a pretty straightforward one. Anybody want to give it a try?
Ethane.
Ethane, exactly. We have 2 carbons, so we know it's an F. And it's all single bonds, no other functional units, nothing else, no double bonds, triple bonds, it's just single bonds, so it's just ethane. Nice and easy, simple. Next, we have G. Anybody want to try this one? This one's a little more complicated, not too much, but we can go through it. So first thing you notice is that it's got a cyclic
Benzene.
hydrocarbon. So let's start naming it. Okay, so we're just going to build this name up together. So what's the first thing that you can think of here? So it's got a 5 carbon unit, 5 carbon ring here. So what do we call that?
Benzene.
It's not a benzene. A benzene ring looks like this one. It's got 6 and it's got double bonds at every other bond. This is a benzene ring. This one is a, let's take a look at our, and jog your memories. I know it's many lessons ago, but it's just that I've noticed that this was something that I saw was causing issues for people. Okay, examples of naming cyclic alkanes. So this is not a benzene because it has no double bonds. What this is a cyclohexane. So we start by numbering how many carbons there are, and then we use the word cyclo in front of it. So this is a hexane because it's 6, and it's a cyclo because it's cyclized. So let's go back to our specific example and see how we're going to name this. So what would this be? This would be a cyclo. Cyclo what? What kind of a? It's got 5 carbons, so it's a
Pent.
pent, and
Pentane.
it's a
or-
pentane. So it's a cyclopentane, but that's not all that there is here. We have some groups added on. What are the groups that are added on? Actually, these 2 are identical. We've got 2 of something. So what else can we write? What is our units that we have added here? These are these are additions, and those additions, we know that we call them alkyl groups. And if you look at that alkyl group, it had 2 carbons, right? So it looked like this. It was an ethyl group, right? It had C2s, 2 carbons, and then 5 hydrogens all around it, right? C2H3. So this is an alkyl group, an ethyl. Right? It's an ethyl. Some sort of an ethyl cyclopentane. Now, how many of these ethyls do we have? We've got 2 of them. So what can we put in front of it to say that we've got 2? Starts with a D. Diethyl, right? We got 2 of them. They're the same. So we've got diethyl cyclopentane. So far we're told that we've got cyclic hydrocarbon, 5 members. So that's the cyclopentane part. We're told that we've got ethyls, 2 of them, diethyl. Haven't told me yet, where are these diethyls? Where are they? Well, we start numbering them based on whatever is the biggest unit. Remember, we start numbering numbering these carbons. So this is a 5-member ring. There's 2 of the same things. It doesn't really matter whether we choose this as carbon 1 or this as carbon 1. But what does matter is if we choose this as carbon 1, we are counting this way so that this can be on carbon 2. We don't want to count the other way and have this be on carbon 5. So if we were to name this carbon, this as a 1,5 diethyl, that would be incorrect. So we can't say 1, 2, 3, 4, 5. No, we want to keep the numbering simple and small. So we want to go 1, 2. So that would be a 2. So this is an example of a 1,2 diethyl cyclopentane. Okay.
So can these have like more than one bond too?
More than one bond? They would.
Yeah, like
Yeah, and then it wouldn't be a cyclopentane. Say you had a double bond in here somewhere. Say one of these was a double bond. It would
so
be
it
a
would have like a line near it.
Yeah, so you would put a
Okay.
line, it would be a double bond in there. And this would be a cyclopentene if it was a double bond in here somewhere. Okay,
Okay, thank you.
yeah, no problem. So, and really, like, it can get more complicated. There can be double bonds in these side groups here and these alkyl groups, but I mean, our level of chemistry right now in grade 12, we're not going to get into that. Just stick with the rules that I've given you and you will be fine. I'm not asking anything more than what we've all the examples, all the lessons we've had so far. Okay, let's take a look at H. Let's look at H, for example. Anybody want to give H a go? Let's just begin somewhere. Where should we begin? What's the first thing we notice? I think Shadissa, you said something earlier.
I thought number that one is a benzene, but benzene. I'm sorry. But
Okay.
you said because this one has 6. What do
So-
you call it? Yeah.
Yeah, so this is the benzene here, right here. So we see a benzene. So let's just start by writing benzene. Okay, so what do we see on this benzene? What have we got? We've got benzene. What else do we have? What are these things? These are alkyl groups on the side. What kind of alkyl groups are there? Let's name this one. What's this alkyl group called? This one is a, anybody want to give it a
Meth.
Thank you, meth. And because it's an alkyl, because it's just joined to the side of, it's branching off, it's a methyl. It's an alkyl group, right? Okay, so let's put a label on this one now up here. So what would that one be called?
Miss, can I give it a try? But I'm not sure.
Listen, we're here to make mistakes and learn. Don't worry.
Is it ethyl?
It's an ethyl, exactly. It's 2.
Thank you.
Ethyl. Exactly, because it's got 2 carbons, CH2, CH3. So it's an ethyl here, it's a methyl down here, and they're attached to a benzene ring. Okay, so now we need to be told which carbon are they on? So let's number them. So which one is the, which one is the bigger one? Is ethyl bigger or is methyl bigger? Which one's going to be carbon?
Ethyl.
Ethyl is bigger. So we pick this carbon here on this ring here. This carbon is going to be our carbon 1. We're going to name this 1. Now, which way should we count? We want, however way we count, for our next one to be the lowest number. So we can either count 1, 2, 3, 4, 5, 6, or we can count 1, 2, 3, 4, 5, 6. So if we count one way, it's going to be 1 and 3. If we count the other way, it's going to be 1 and 5. Which one should it be? Should it be a 1 and 3 or a 1 and a 5? Who wants to take a stab at this one?
1 and 3.
1 and 3 is better than 1 and 5. Yes, we want to keep numbering simple. So 1 and 3. So our ethyl is going to be on carbon 1. So it's a 1 ethyl. And our methyl is going to be on 3. So it's a 3 methyl. So now let's put our name together. We know our benzene is going to go at the end. Then we've got to figure out, okay, so is it going to be methyl and then ethyl in front like that? So it's going to be 1 ethyl, 3 methyl, or is it going to be 3 methyl, 1 ethyl? Okay, so how do we choose which one will come first? What's the rule there? Does anybody remember the rule?
Is the bigger one first?
It's the alphabet that tells us which one comes first. So
Oh.
the bigger one tells us which one is going to be carbon 1, the carbon 1. And because this one was bigger, this carbon that it's attached to became carbon 1. But in terms of putting them in the name, it's the alphabet that tells us. So our alphabet tells us that, so we look at this, we look at what letter does this begin with? This begins with M, this begins with E. Which one should come first? Should 3 methyl come before 1 ethyl, or should 1 ethyl come in front of 3 methyl? Somebody want to name this? Say that again.
Ethyl, methyl, benzene. Like, sorry, 1 ethyl,
Perfect.
3 methyl, benzene.
Exactly. Thank you very much. So we name it 1 ethyl, 3 methyl, benzene. And we go ahead and would put a comma in there when we're separating those. Exactly. So that's how you name that kind of thing. Okay. Everybody feeling good about this? Okay. What time is it? 7:15. Oh gosh, we got tons of time. Okay, we're gonna do one more, and then I'm gonna move on to another set of support questions that I think you guys should get some practice with. Okay, let's try this last one here. This I. Okay, so what do we see? Where can we start? Something we can start with.
It's a benzene.
There's a benzene ring. Thank you very much. Okay, so we have a benzene ring. So let's write that down. Like you said, oops. So let's write down our benzene. Benzene. Okay, what else do we have? What's attached to the benzene?
Really long. There's 3 things attached, I think.
Okay.
No, 2.
Okay. Or we can think of this, maybe the easier naming. I mean, naming this, then this becomes like a branched hydrocarbon off of the benzene. So that might be a little bit tricky to name. But another way we could name it is we could have 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, 7. And we can name our longest parent hydrocarbon chain, and then we can treat these as the groups that are added on, right? So when benzene is added on as a group, the other name for it becomes phenyl. Thank you. Yes. Thank you. Becomes phenyl. So I'm going to write that down right here. Oops. Phenyl. It's when benzene is a group that's added on. It's a phenyl, right? So we have something. So how do we name this? First of all, pick which chain are we numbering. Here we've got 1, 2, 3, 4, 5, 6. Do we pick this one, or do we follow the other branch? 1, 2, 3, 4, 5, There's 2 more carbons here, 6, 7. So do we want a 6 carbon chain as our parent, or do we want a 7 carbon chain as our parent?
7.
Exactly. We always want to pick the longest one, even if it may not be straight in our picture. Follow the bend if that's what gives you the longer hydrocarbon chain, the longer parent chain. All right, so we've got a 7 carbon hydrocarbon chain. How do we name it?
It's a heptane or
It's a heptane. Thank you. So we take our phenyl and we have our heptane. What else do we have? So here's our heptane part. Here's our phenyl, the benzene ring that's attached. We call it phenyl. Then we got something else here, a little guy here.
a methyl.
That would be our methyl, yes. It's an alkyl group. It's 1 carbon, so it's a methyl. Okay, so we have methyl, we have phenyl, we have heptane. How are we going to put it all together? How do we number this?
Was it like the longest one gets on 1 and the other one like we see like, is it gonna be like, let me see.
Okay. So in this case, it's not the longest one that gets the number. We try to see which one gives us the smaller numbering. So we try to see which numbering. So 1, 2, 3, 4, 5, 6, 7. So that would make this be on 3 and this one be on 5. So it can be a 3, 5. Or if we count this way, it can be a 3 and a 5. So either way, the numbering will be 3, 5. So our numbering, either end we start with, whichever carbon end we start with, is going to be a 3, and then whatever it is, and then a 5. So we know either we start at this carbon being 1, 2, 3, or we start at this one being 1, 2, 3. Either way, our attachments are at carbon 3 and carbon 5, or carbon 3 and carbon 5. So then how do we decide then if which one of these actually should be 3, could be 5? Because they're not identical. One of them is a methyl, one of them is a phenyl. If both of them were phenyl or if both of them were methyl, it doesn't really matter. Pick one. But here it does matter. They're not the same. So which one do we choose to have the lower number? The methyl or the phenyl? Let's look back at our examples. Let's see, where was I? Anybody want to?
Which one was the 3 one?
So you have to decide which one is going to be the 3 one.
Oh, okay.
So which one is going to be the 3 one?
The methyl.
Okay, so however, because the numbering of the parent changed so that the substituents is attached to the carbon atom with the lowest possible number. And if there's 2 or more groups and numbering is a tie, so that's the case in our example, numbering is a tie, the group that comes first alphabetically gets the lowest number here. Okay, in this case, let's look back and see which one is the one that gets the lowest number. So either way we count, one of them is going to be on 3, the other one's going to be on 5. Or if we count at this end, this one's going to be on 3, this one's going to be 5. So we can't improve our 3 and 5 number. It's a tie. So now we just got to decide alphabetically, should methyl be the 3 or should phenyl be the 3? Which one comes before in alphabetic? A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. So M comes first alphabetically, right? So 3 goes to M, right? And then 5 goes to the P. So 5, comma, right? And excuse me, we don't put commas there, we put dashes. Okay. So now we've got our numbering sorted out. Now, how do we put it together? Now what goes where?
Is it 3-methyl, 5-phenylbenzene?
Exactly, because again, we put the one with the alphabetically first. Then we put our, whoops, got the wrong one. Then we grab our, then we grab this one, methyl 5-phenyl. Poster. And we can delete this benzene part because we talked about it. And then we put our heptane in there. Boom. We put a comma. And guess what? Now we are done. So the name of that is 3-methyl. Here's the methyl on carbon 3. 5-phenyl. Here's phenyl on carbon 5. And it's a heptane. Okay, everybody feel good about those examples we just did? It's a little bit confusing, but go through and there's these tutorials that I actually copied straight out of your textbook. And they really explain, they go through the same things I said, just give you more examples of things that you can practice with. These are here from the previous time I taught this course. There were some questions some students had, and I just referred them to these tutorials that are straight out of the textbook that really help them to, again, review the rules and figure out how to name things. Okay, so, oh, here we go. Was it Sasan that you were asking about what if there's a double bond in the cyclic hydrocarbon ring? So here's an example of what if there is a double bond. So here you see it's a cyclopent, but because there's a double bond, it's a cyclopentene, right? Yeah. So yeah, I know somebody was asking about what if there's a double bond. So yeah, this would be, so here's an example of that parent chain. It's a 5-carbon atom, it's a cyclopent, but because there's a double bond here, it's a cyclopentene. And then it has this methyl group. But in this case, because the double bond takes precedence over the alkyl group, first we need to do our numbering, excuse me, so that the carbon that has the double bond gets the lowest number. So here, this doesn't become carbon 1. One of these becomes carbon 1. And if one of these becomes carbon 1, then it becomes 1, 2, 3, 4. So that's why our numbering is 1-ene. So we indicate that that's where that double bond is. It's on carbon 1. So cyclopent 1-ene, and that the methyl group is on carbon 4. So 4-methyl cyclopent 1-ene is how you would correctly name this. All right, in a carbon, in a ring, carbon atoms are always numbered so that the multiple bond, the double bond, is between carbon atoms 1 and 2. We always want that to have the lowest number. So yeah, these are really useful examples. They're here because they illustrate certain points. So go through them and you'll understand this some more. Okay, we are at 7:30. I'm gonna continue with something else. Let's see, what can we do here? All right, let's look at these, some more support questions. Naming of molecules. Okay, these are super easy. So again, if you know how to name them, you will also know how to draw them. And one thing I noticed that some of you were doing on your key questions, it really helps. It helps you. It helps you not make any mistakes to go ahead and write every single C bonded to another C bonded to an H. Go ahead and put all these details in there instead of just drawing a zigzag, 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 zigzag line, because then you get confused. And double check by counting. Count your carbons. 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons here. 8 carbons here and an alcohol group. So this has got to be something all. What kind of an all? What kind of a prefix tells us that it's 8 carbons? Anybody?
Sorry, can you say again?
Yeah, so how would you name this one, for example?
Was it like, I kind of forgot, was like counting the smallest C's till it reaches the OH?
So yeah, you want the, first of all, you want to figure out how many C's do you have? And start naming your parent chain. So how many C's do we have?
I think we have 8.
Okay, we have 8. So how do we name it? So the parent base should be
It's octane.
octane. Now you notice that it isn't just an octane, it's got an OH group. It's got a hydroxy group here on it. So what is it? It's an octa. How do we name alcohols? Alcohols, so it's an octane, but we drop the ane and we put all. So it's an octanol, right? It's an alcohol, octanol. So great, we know that it's got, the name is telling us 8 carbons and alcohol. But what the name still hasn't told us is, where is that alcohol? You got a choice of 8 carbons for it to be on. Where is the alcohol? So we start choosing which one is going to be carbon 1. And how do we choose which one is going to be the carbon 1? Well, let's see which one will give us the lowest number for this. If we start from this end, we get 1, 2, 3, 4, 5, 6, 7, 8. So this, starting at this end as carbon 1. Oh goodness, my battery's running low. At this end, I'm gonna have this as on being on carbon 5. If I start counting from this end, then I'm going to have this on carbon 4. So where do I want it? Do I want 4 or do I want 5? Which one's the correct way? So we so far said it's an octane, but then because of the alcohol, we say it's an octanol. And because we have to say where is the alcohol group on, what number should I put in front of it? Is it a 4-octanol or is it a 5-octanol? Which one's the better choice?
Maybe lower.
Lower, exactly. The lower is the better one. So this one is a 4-octanol. No problem. 4-octanol. That's what we've got here. Okay. How about this molecule here? What type of a molecule is it? We've got a bunch of hydrocarbons on this side. We've got hydrocarbons on that side. Then we've got an oxygen in the middle. You guys remember? That is ether, ROR. That's an ether. Some hydrocarbons on this side, some hydrocarbons on that side of the oxygen. So this one is an ether. We know that whatever it is, it's an ether. So now we've got to name this side and we've got to name that side. So what kind of an ether is it? It's got a methyl group and it's got a propyl group. And we can name it as methyl propyl ether. This one is a methyl propyl ether. Okay. Or we can call this, I mean, that gets more confusing. I would just rather you call it a methyl propyl ether and stop yourself from getting more confused. But you can review the two methods of naming them. You can either name the longest alkyl as the parent chain and then put oxy at the end, so that in this example,
Sorry, I lost voice and everything.
No, you didn't. Miss Nigel left.
Oh, wait, what? Then why is it saying Jude? Oh, it's, wait, what? That's weird. He changed the host too. اما باید چیکار کنیم؟ فکرم کامپیوترش ویروس گرفت.
نه شارژش تموم شد.
باز بهتر ببینیم. خوب باز ویروس هم. چه یهو ترسناک یه چیزی اومد اونجا رو بعد یهو تمام. عجیب بود. کسی شماره معلوم داره؟ یا نه ایمیل
نه
بزنیم ببینیم شاید مثلا معلوم هستم شاید قاد بزنن نه اجازه نده نمی‌دونم. میشه اصلا هست
ایمیل
عوض کرد
ایمیلشو داری؟
ایمیلش آره دیگه اون به اون پیغام میده بندم
آره
ایمیل
دیگه
بزنیم
از چه ایمیلش کردی؟
دوستان من مطمئنم اگه میتونست برگرده تا الان برگشته بود. یکم منتظر بمونیم برمیگرده.
پس میتونه برگرده تو اینجا. فقط من گفتم من هستم شب قاطی همه چی. الان منو هست کرده برای این. من گفتم شاید اونجوری شده باشه اصلا دیگه نتونه کار
نه
کنه.
خودش اصلی است، چون هنوزم نمیدونم جلوی شما الان چی هستش، ولی جلوی من این میتینگ تاپیک و هست و دیگه پسکود و اینوایت لینک و اینا هستش، هنوزم برای من هست نگاه هانگه بیشی بی اوکی.
با اوکیه. اصلا الان چکه هم میتونم هست رو
اگه
برگردونم.
خودمونیم هممون به نظر من یه دونه گروه واتساپ نداشته باشیم از همدیگه سوالی چیزی داریم.
اونم خوبه، فکر خوبیه. teacher is back.
Okay, sorry about that, guys. I didn't have my power supply with me.
No problem.
Okay. So, let's see, where were we? Okay, can everybody, no, I'm not sharing screen anymore. There we go. Let's get that. Okay, can everybody see where we left off on our support questions again?
Yes, I can see.
Okay, perfect. All right, so I apologize very much about that. I could see the low battery sign, but I was also hoping that it would hold out for the next little bit. Okay, we still have 20 minutes. So, right, so we were talking about this one, and there's two names that you can use to name ethers. Ethers, you can either name the longest one as the oxy, so 1, 2, 3, prop, oxy. So methyl propoxy would be one way of naming it, or you could name it as not methyl propoxy. What am I saying? You can either name it as the propane as the longest parent chain here, and then that one would be the methoxy, or you could name this as methyl propyl ether. That would be probably the most straightforward way of doing it. Just go alphabetically. Methyl comes before propyl, so methyl propyl ether. Okay, that would be another example. So yeah, review and remember how to name your groups, your carboxylic acid groups. Remember that if you have this COOH group, it's a carboxyl group, and it gets an ending of oic acid. So this one, for example, butanoic acid, because of the COOH here. You've got the benzene with a COOH on it, so benzoic acid. That one's one. Esters, yeah, again, the same rules apply everywhere. Review them. And types of reaction. Okay, so here's another area that I found that students needed to review. So based on the key questions that were handed in, I think everybody needs to really review and understand what is the hydrogenation reaction and where do the H's go, review halogenation reactions and understand the rules as to where they go. There needs to be a double bond. Once these are in there, then it's no longer a double bond, it's a single bond. Hydrohalogenation reactions, or even when you have the addition of a water. So anytime you've got something that you're adding that the two sides aren't the same, that we've got two different atoms being added to the double bond, you follow this Markovnikov's rule to decide which carbon gets what. And the rule here, if you remember, was rich gets richer. So the hydrogen atom goes to the carbon atom within the double bond that has already got more hydrogens on it. So it won't go to this one, it'll go to this one. This is the correct structure, okay? Because if you look at here, this carbon has already got two, this carbon has only got one. So the rich gets richer. The hydrogen here goes to the carbon that already has more. It's already richer with hydrogens, it's going to get richer. The hydrogen goes there. Rich gets richer. Markovnikov's rule. Then, okay, substitution reactions, pretty straightforward. Okay, combustion reactions, yes. So I noticed again from the key questions that, and I really tried to emphasize it in today's lesson that we did about what are combustion reactions. So what I really want everyone to understand that in combustion reactions, whatever is reacting, it's reacting with oxygen and it's going to carbon dioxide and water and energy, of course. And then you have to balance how many carbon dioxides, how many water, how many oxygens to account for everything that is on the reactant side has to add up to everything that is on the product side, whether it be a sugar molecule, whether it be an alcohol that is being burned, or some sort of an alkane that's being burned, or whatever that's being burned in this combustion reaction is reacting with oxygen and it's giving carbon dioxide and water. And then you have to make sure you put the right numbers in there to balance the equations. I think you should remember how to balance equations from previous chemistry courses. Oxidation reduction reactions. Looked at those in great detail. I'm trying to think of what else we can talk about. So what type of support questions were we asked here? All right, yeah, write a balanced equation to represent the combustion of these hydrocarbons. Do you guys think you want to take a stab at some of these equations? Because I noticed that there were some mistakes on the key questions of this.
Sure.
Yeah, so let's do that. Okay, I'm just going to bring my answer up so that I'm not giving you guys the wrong answers. Okay. Right, so the combustion of ethane. So what should we start by writing? Ethane is what type of molecule? How many carbons?
It's one bonded and C2H6.
Right, it's C2H6. So you can either write it as that, as C2H6, or you can go ahead and write your, carbon bound to hydrogen, and on this side, hydrogen bond, and then up here you would put two more carbons. A lot of times just doing that, it makes it easier to see what is happening if you're asked to write the structural formula. You do that. Otherwise, I'm okay if you just want to write the C2H6. And what is it going to react with? It's going to react with, it's a combustion reaction. So
With water?
it is in a combustion reaction. Think about combustion. What does combustion mean? Combustion means burning. When you're burning, what do you need?
Heat, so
We need oxygen.
Yep.
Right? We need O2. And then it's going to go to, let's imagine this is my arrow. It's going to go to, what is it going to give us? In a combustion reaction, you get something that's burning with oxygen. In this case, it's our ethane. And in a combustion reaction, you get nothing except what at the other end? It's if it's a complete combustion, which in these ideal chemical equations, we are talking about complete combustion. What do we get? We get, all right, let's go back and take a look.
is it gonna be H2O plus energy or?
Yeah, H2O would be one of them. We get water, and we get water often in the form of water vapor, right? And what else do we get other than water? When you burn something, what gas is produced?
Carbon or?
Carbon dioxide. Yes, exactly. Carbon dioxide is produced. Very important things to remember here is in a combustion reaction, whatever you have here, this can be whatever. You have it reacting with oxygen, you have it giving you carbon dioxide and water. Okay. So then what do we have to do with this reaction? Is it good to go? Is this reaction good to go? No, not even close. What do we have to do? Is it balanced? How many carbons do we have on this side?
2.
2. Do we have 2 on this side?
No.
No, we don't. Let's put a 2 there. So we have 2 carbons. Boom. Okay. How many hydrogens do we have here?
6.
6. Do we have 6 here? On
No.
on the product side, do we have 6?
No.
How many do we have?
We have 2.
We have 2. Thank you. What coefficient can I put in front of H2O to give us 6 hydrogens?
Four.
So if I put
4H.
4,
4H, I think, like H4.
so if I put 4 here, 4 times 2 gives us 8. Is 8?
Oh, sorry,
How
3.
many we need? How many? 3? So 3 times 2, that makes 6 hydrogens here. We have 6 hydrogens there. Okay, hydrogens are balanced. This is looking good. Let's check our oxygens. Okay, here we have 2 oxygen, O2. Okay, here we have, let's see, we have 2 here, but because we have a 2 here, so it's 2 times 2, that's a 4, right? So 4 oxygens from here, and then we have 1 oxygen here, but then there's a 3. So we have 3 plus 4. How many oxygens on this side?
We got 3.
3 plus, how many oxygens are coming from our CO2?
2.
2, but we have 2 of them. So that means altogether here is how many? 2 times 2?
4.
4 plus 3?
7.
7. So we have 7 oxygens on this side. We have 2 oxygens on this side. Is it balanced?
No.
No. What number can we put here? Can we put a 7?
No.
No, because 7 will give us how many? 7 times 2. That would give us 14 oxygens. We don't have 14 oxygens. We have 7 oxygens. So what can we put? we can put a fraction. We can put 7/2. 7/2 times 2. That makes us have 7 oxygens. Now we have 7 oxygens. So now our equation's balanced. We've got 2 carbons. We've got 6 hydrogens. We've got 7 oxygens. And if we add up these and these, 7 oxygens. Now our equation is balanced. See, write a balanced equation to represent the combustion of the following hydrocarbons. So this is for the ethane. Okay. All right.
Okay.
And you should be able to do the same for the heptene, the 2-heptene. So again, you start figuring out, so what is your formula? And maybe you can't right away jump from here to the formula. Maybe you have to draw out your carbons and hydrogens and all the bonds and figure out there's a double bond in there. So then I don't have as many hydrogens as I would if it was just an alkane, because now it's an alkene. There's a double bond in there. That takes away some hydrogens. So you want to really write it out and figure out how many C's, how many H's. And then you do the same thing because it's a combustion reaction. So in a combustion reaction, what are the 3 things that you need? You need everybody say it together. Everybody say it together. We need oxygen. We need carbon dioxide,
Yeah.
not just carbon dioxide. We need carbon dioxide. And we need
water.
Water, exactly. So these are the 3 things that are going to be together with whatever else we are combusting. That is going to react with O2. It's going to make CO2. It's going to make H2O. And then finally, we have to balance it. And then you just balance it like we just did in this example. Okay. What else? Draw the structural formula to show each of these addition reactions. So if you have 2-butene and hydrogen gas, or 3-hexane and bromine, or draw the formula to show the formation of the following esters. Okay, I'm trying to see which one of these is a good one to do for you. Or even these, write an equation to illustrate each of the following equation: the substitution reaction of propane, halogenation of benzene, or preparation of 3-pentanone from an alcohol. All right, let me see what I've got. I have got okay. Let's take a look at this in our last few minutes. Okay. So draw the structural formula to show each of the following addition reactions: 2-butene and hydrogen gas. Okay, so 2-butene. So 1, 2, 3, 4. You know, you've got 4 carbons. You know, there's a double bond here. Why is that double bond not showing up very well here? I'm just going to go ahead and add it in to make it a little more clear. Boom. Okay, and then our hydrogen gas. So this line should actually be here. Didn't come out well. So then what happens here? It's an addition reaction. It's a hydration, not hydration, hydrogenation reaction. These 2 hydrogens go to these 2 carbons. So you get CH3 bound to a CH2 bound by a single bond Again, I'm not sure why these didn't come out well, like that, let's say, bound to the CH3, okay? Next example, 3-hexene and the bromine. So hexene, the hex part tells us it's 6 carbons. So you put 6 carbons, 1, 2, 3, 4, 5, 6. The ene part tells us there's a double bond in there. Where is the double bond? The double bond is on carbon number 3. This is what that 3 tells us. So we put it on carbon number 3, 1, 2, 3. That's where it goes. And bromine. Bromine is a diatomic gas, Br, bound to another Br. And this is a halogenation. So just like the 2 H's went to these 2 carbons on either side of the double bond, the bromines go to these 2 carbons on either side of the double bond, and you don't have a double bond anymore because the bond with the carbon got used up for the addition of the bromine. So this is an addition reaction. It's a halogenation, okay? So draw the structural formula. And whenever I say structural, I mean structural. Draw me the structure. I don't just want to get, you know, CH3OH. I want to get C, line, 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 H, 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 O, line, H. That is a structural formula, guys. So draw the structural formula to show the formation of the following esters. So methanol and ethanoic acid. So methanol, pretty simple. Meth, 1 carbon. It's a methane, 1, 2, 3 there. On the, instead of the 4th bond being an H, it's an ol. So it's an alcohol. So we put an OH group there. Methanol. And draw the structural formula to show the formation of the following esters. So we put our plus and we write our other component, which is the ethanoic acid. So F, 2 carbons, oic acid. So we put our C double bond O and the OH, COOH. This is a carboxylic acid. It's an ethanoic acid. And then what happens when we get the ester? The ester, there's an elimination reaction, a dehydration, the water is removed. So we lose an H and we lose an OH and we get this molecule here, okay? The same with this example here. Okay, so it says write an equation to illustrate each of the following equations. The substitution reaction of a propane. So substitution reaction is when one of these swaps for one of those, okay? So the Br goes here and the H comes here. They swap places. A halogenation reaction of a benzene. Okay, we draw a benzene halogenation. So a halogen, pick a halogen, anyone. It could be fluorine, it could be iodine, whatever you want, bromine. Let's pick fluorine. So where does it go? It goes on either side of that double bond. So one of them goes there and the other one goes here. Okay. Oh. What else? Okay, I think it's 8:02. I think we covered quite a bit of review material here today, but I think that was important because I could see that some of the concepts weren't coming through. So I really want everyone to spend some time looking at your lessons, looking at your support questions, and ask questions. Ask questions. Okay, come to me with material that I can then talk to you about. Talk to the whole class about. Because guys, don't forget, if you're having a problem with it, chances are other people are too. So, and don't be shy about making a mistake. Don't worry about, oh, am I the only one who doesn't get this? Am I going to sound silly by asking this? You're not. We're here to learn, and we're here to learn all together. But if you are shy and if you don't want to do this within the class in front of everybody, we can do this through email, or we can talk before class or stay after class. Let me know. As always, it's my pleasure to teach you. Have a good night, everybody.
Thank you. Have a great night.
Thank you. You too.
Have a great night, ma'am. Bye-bye.
Goodbye.
Bye-bye.